Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to network theory, circuit theory, and we'll keep our discussion focused on network theorems. So far in the previous few videos we discussed about reciprocity theorem. So in this video we will discuss about another important network theorem which is called as Millman's theorem. Okay, so before going into this theorem discussion into detail, I want you to please watch the videos on Thevenin theorem, and Norton's theorem. Okay, these two. Why? Because these two theorems are very much important in the discussion of Millman's theorem, or we can say that the Millman's theorem is actually based on Thevenin's and Norton's theorem, and we want to get the result in terms of Thevenin and Norton's theorem. Okay, that's why it is very important that you are very clear about Thevenin theorem and Norton theorem. Suppose we have a situation where we have a circuit like this. Like this, we have a circuit. Okay, like this. Okay, let's call them like this. Okay, 3 R3, R4, R5, V4, R6, like this. Okay, we have a circuit and we have to simplify it, or let's say we have a final thing and we have to find out this current like this, any kind of a manipulation associated with it, any operation. So this circuit is very complicated to handle when we apply normal circuit analysis techniques, be it mesh analysis or nodal analysis, or if we try to apply normal superposition theorem or Norton's theorem or Thevenin's theorem directly, it is very difficult. Okay, because it will produce a lot of equations, each associated with all of these individual nodes. If we go for nodal analysis, also each of these closed loops will produce loop equations. Solving such equations, such number of equations involving a lot of variables, it will be very difficult and it is practically not possible. So this is one situation. Another situation is like this. Like this, we have a circuit. Let's say these are the current sources, R1, I2, R2, I3, R3, and let's say this is nth current source, nth source. Also solving these kind of circuits, it is very much difficult. Okay, Same problem, lot of equations, lot of variables, and that's why it is very difficult. Suppose there would have been, a way by which we can convert this whole complicated circuitry into a simplified representation. Okay, this also. Let's say we can convert it into this form. Okay. Like this. We can convert all of this into this form and all of this into this form. That would be very easy to handle. So this is the whole point of Millman's theorem. Okay, so if you remember, this is the Thevenin equivalent circuit, the Thevenin representation. This is the Norton representation. And if you watch all of these circuits closely, each of these voltage sources and resistors connected in series, they are representations of Thevenin representation. Okay, voltage sources connected in series with a resistor like this. Okay, and here all of this, a current source connected in parallel with a resistor, that is the Norton representation. All of this also, all of this, it is Norton representation. So we are just combining all of them, converting it into a simple form. That is the whole point of Millman's theorem. So we can discuss Millman's theorem in two parts. Okay, Millman's theorem we can discuss in two parts. First part, parallel voltage sources, and the other one is parallel current sources. Okay, so let us first discuss the parallel voltage sources. So parallel voltage sources, it refers to this arrangement: voltage sources along with resistors, that series combination, and a number of such combinations connected in parallel. So this is the arrangement, a typical arrangement. Like this. Let's call them R1, R2, R3. This is the nth resistor. This is Vn. This is V3. This is V2. This is V1. So here, if we want to convert it into a simplified form, particularly the Thevenin equivalent form, like this. This is the format to convert it into a simple form. Then the value of VTH will be, VTH value is V1 by R1 plus V2 by R2 plus V3 by R3 plus dot dot dot, any number of voltage sources are present like this, divided by 1 by R1 plus 1 by R2 plus 1 by R3 to 1 by Rn. This is VTH, this one. RTH is simply the parallel equivalent resistance. RTH is R1 parallel R2 parallel R3 to Rn, this, which is equal to 1 by R1 plus 1 by R2 plus 1 by R3 1 by Rn, this. So how did we come up with these results? So let us prove it. So we'll not take these many voltage sources and these many branches. We'll just prove it using 2 voltage sources and 2 resistors in order to minimize the number of equations. Also, if we take more number of voltage sources and resistors, we can get the results, but it will be a lot of time it will take. So just let us take 2 voltage sources and 2 resistors. This. We have to determine the Thevenin equivalent circuit of this. Okay, Thevenin equivalent circuit. So for VTH, what we have to do, we have to determine this open circuit voltage. Okay, this open circuit voltage, that is VTH, keeping all the independent voltage sources intact. Okay, this. So this is VTH. This is VTH. Okay, so let us say a current I, mesh current I, flows through it. So if we apply KVL in this closed loop, it will be, the KVL equation will be V1 minus IR1 minus IR2 minus V2 is equal to 0. That implies V1 minus V2 is equal to I into R1 plus R2. That implies I is equal to V1 minus V2 by R1 plus R2. This is very important. This equation is very important. Now, if we apply KVL in this outer, this loop, this where we have to find out the Thevenin voltage, this equation will be VTH minus IR2 minus V2 equals to 0. Okay, in this way, in this direction we are putting it. Okay, VTH minus IR2, because current I is flowing through it. Okay, then here we have minus V2, the second sign dominating method we are using. So please watch the videos related to basic circuit analysis techniques, where I have discussed about KVL, KCL, mesh, nodal, everything. So I am not going into detail. That implies VTH is equal to IR2 plus V2. Here, in place of I, will substitute this value, V1 minus V2 by R1 plus R2. That implies VTH is equal to V1 minus V2 by R1 plus R2 into R2. Here in place of I, we have substituted this value plus V2. That implies VTH is equal to, opening the bracket, V1 R2 by R1 plus R2 minus V2 R2 by R1 plus R2 plus V2. This, okay, like this. Then further simplifying it, that implies VTH is equal to R1 plus R2, common thing, V1 R2 minus V2 R2 plus V2 into R1 plus R2. This. That implies VTH equal to V1 R2 minus V2 R2 plus V2 R1 plus V2 R2 divided by, okay, let us just expand it a bit. Okay, this will be sufficient, by R1 plus R2. So here V2 R2 and minus V2 R2 will be cancelled. So this is, let us bring it here, VTH is V1 R2 plus V2 R1 by R1 plus R2. Okay, this, but this is not the format which we did here, we got here. This is not like that. So in order to bring it in that format, let us divide R1 R2 in both the numerator and denominator, that is V1 R2 plus V2 R1 divided by R1 R2 by R1 plus R2 divided by R1 R2. That will be equal to V1 by R1 plus V2 by R2 divided by, okay, 1 by R1 plus 1 by R2. Okay, this, isn't it? So as there are only two voltage sources and two resistances, that's why we got this result, which is this. Here, as we have considered nth voltage sources and nth resistors, that's why we got this result. But here, for simplifying the result, for keeping the number of equations involved is less, that's why we took only two voltage sources, two branches. So we have got this result, which is VTH, which is the value of VTH. Now for RTH, for Thevenin resistance calculation, we know that that is done deactivating all the independent sources. Now we know voltage sources are short circuited, current sources are open circuited. So here there are two voltage sources present. So for that, what we have to do, we have to determine RTH short circuiting the voltage sources. So it will be R1, this V1 short circuited, and R2 with V2 short circuited, and that means RTH is simply R1 parallel to R2, okay, and that is equal to 1 by R1 plus 1 by R2, that. So this is RTH and this is VTH. So just to prove it to you how we got these results, I did all of this. Suppose you would have taken 3, 4, 5, 6, 7 voltage sources, we have got the same result. But in that case, there would have been a lot of equations and everything. So it would have unnecessarily complicated the whole thing. So we just wanted the proof, that's why we did this. Okay, so this is the Millman's theorem with parallel voltage sources. Okay.